exponential.
Okay, the topic of the day is integration by substitution. This is our first foray into our first advanced integration technique. So this is good. This is a good, big day. What do we do with this?
You put some calculus in it, and it's good.
What kind of what octane calculus you can put in this here?
High test.
Okay, what's the problem with this? What's complicated? Yeah. Now, let's think of the very limited repertoire of tricks you have here. We only have a few calculus antiderivative rules that work. Now, do we have one similar to this that works?
Yeah, sure.
Kind of, right? I mean, it's what if the fives weren't in there, for example? We could do this then, couldn't we? Right? If we know antiderivative of cosine x dx is what? Well, sine x plus c, right?
Yeah.
Okay.
Nope. Roll backwards.
And I could say if I want, it doesn't even have to be an x, does it? It could be something instead, like what if we said cosine of u du, that would just equal sine u plus c, right? Okay, but that's not what we have, is it? In purple. So, can we do that one?
Yeah, I think we can.
I like the enthusiasm.
Yes, we can.
Yes, we can, but it doesn't fit one of our standard forms as it's written, does it?
We learned something.
Okay. Anybody have any ideas?
You take the 5 out, put it.
Okay, we could take this 5 out if we wanted to. That's an option, right? But what about that 5? Say it again. Okay, you know what? We're gonna do something like the chain rule. Exactly. We're gonna do something. This is sort of the integration equivalent of the chain rule. We can't take that 5 out of the cosine because it's stuck inside the cosine function. This other 5 is just a constant multiplier, right? It's just attached to this whole function by multiplication. So we could just pull that out front like any constant. But not this one. And so we do need something like the chain rule. All we're going to do here is something in math that seems so simple, but it's really powerful. We're going to do something called a change of variable or a variable substitution. What if we want to make this integral look like that one? What variable substitution would I have to make?
U.
U equals what?
I think.
5x. Yeah, so simple. Let's try that. If u equals 5x, then look what we get there. We get a cosine of u. Now that's looking pretty good, isn't it? Cosine of u looks like something we can deal with, almost. But if I just make that substitution, excuse me, we end up with 5, yeah, there you go, 5 cosine u, whoops, times dx. Now that's a mess, right? That doesn't look like any of the integrals that we've done. Something is drastically wrong there because the variable of integration has to match up with this variable, right? So what do we still have to do that we haven't done yet? We can't just go part way with this, can we? We have to complete the whole substitution. So I need to get it to look something like this. I need to get a du, but how am I going to get a du? Now look though, I just defined what u is in terms of x. It's a variable substitution. So if I want to get a du, any suggestions? What? Say it again. It's okay. Du dx would be, yeah. So now hold that thought. So if we do du dx, that equals 5, doesn't it? right? But what we really want to get is just a plain old, in these integrals, the derivatives are always written in differential form. They're not written as a ratio, are they? Right? So if I just solve this for du, what do I get? 5 dx, right? Okay, so du
You get 5 du.
equals 5 dx.
So we can plug it in instead of.
Yes, exactly, right? And I would argue that you don't even need this middle step. You can really just skip that, and you can just do the derivative in differential form, right? Does that make sense? You're welcome to do it this way, but really we could just say the derivative of u, if I'm not taking the derivative with respect to anything, we're just doing the derivative in differential form, we'd say the derivative of u, 5 is a constant, so we just get 5 times the derivative of x. Right, the same rules still apply, but we just don't differentiate with respect to anything, right? Okay, now we can make our substitution directly, can't we? We've got a cosine u, and look at this. Here is a 5
That cancels out.
dx, so that can all get replaced with the du, can't it? Right? See the point?
No.
Okay. So then we can write this as,
It can get replaced with what?
well, we just found out that du equals 5 dx, and there's a 5 dx.
Oh, okay, so it's just du cosine u.
So it's cosine u
ut.
du. What's the answer to that? Sine u plus c. But really what we wanted to find was the answer to this integral, which is written in terms of x. So now what do we have to do? Change it back. Yeah, reverse the substitution. Right? And so we end up with the answer sine 5x plus c. Okay? So that is what people oftentimes call a u substitution. It doesn't have to be u, but just for some reason that's what we sort of use in calculus. But it's integration by substitution. We're going to make a good substitution that allows us to fit a more complicated chain rule type problem. Because really this is, and why do we do that? Because we've got a composition of functions, right? We have a function of a function. Instead of this just being a one-layer deal with a cosine of x, it's a cosine of the function 5x. But if we make that u substitution, everything worked out, right? So we were able to trim this back to look like a single layer problem. But really all it is just a chain rule problem, okay? Let's try another one. Okay, what about, I'll tell you what, I'll pick some just that are in the books. You don't even have to write these down if you don't want to. Just kind of watch this. You can go look at these later if you want to. How about something like this guy? Okay. 2 questions. Could we have done this one yesterday? Yeah, how could we? Well, okay, but as it's written, it looks complicated. It doesn't look like one of the standard forms. But I could have expanded it out and gotten a polynomial and just integrated term by term, right? Okay, so we could have, but we would have had to do some algebra to do that, right? We would have had to expand out that binomial, collect terms, and then do a whole bunch of little integrals, right? Okay, today, can we avoid that?
Yes.
Okay, how can we avoid that?
U substitution.
What's our u going to be? X squared plus 1. Yeah. There's a little bit of an art to this u substitution business. Typically, though, you're gonna get good at this really fast. Typically, the u is going to be the argument of some other function, meaning the inside of some other function. So in this case, whatever is being taken to a power is a really good choice for a u. A lot of times, if there's a trig function, the argument of the trig function is another good candidate for a u substitution. And what's the worst thing that can happen if we try a u substitution? Doesn't work. So what? Try something else, right? I mean, a lot of that happens in math, honestly. So let's pick this one. What if u equals x squared plus 1? Now we got to complete the substitution and see if our du also works. So what is du? so the derivative of x squared plus 1, derivative of 1 is nothing, right? But the derivative of x squared is 2x, and because it's in differential form, we have to add that dx there also, right, by the chain rule.
So we just switch
Yeah,
it
the
out.
derivative of x squared is derivative of hand squared is 2 times hand, then the derivative of hand in this case is just a dx, right? Same thing as adding the intermediate step, finding du dx, and then multiplying both sides by dx. Very same thing. This is just quicker. Okay? So are we able to make what we call a complete substitution here? Yeah. Okay, so this works, doesn't it? So we're able to trade this for the integral of, u squared du, which is what?
2x dx. No.
X squared plus 1 squared.
Okay, but let's do it in terms of u first. So u to the third over 3 plus c,
you're
good.
taking the end.
So if we reverse the substitution then, we get the quantity, x squared plus 1 cubed over 3, or 1/3 times, however you want to write it, either way. Let's see. Is that not cool? That's really cool. That just takes everything you've learned and just amplifies it massively. Now you can not just deal with these few hand-picked functions that happen to match the standard forms. You can deal with lots of different stuff, right?
Okay, so you just put the x squared plus 1 back in instead of u.
Mhm.
So that's the answer right there.
That's the answer, yeah.
Okay.
Yeah, because now essentially what we're doing is we're transforming variables to make the integral easier to do, but then we gotta reverse the transformation to get back to the variables of the original problem. Okay? All right, let's try another one. How about okay, so what would our u probably be in this case? X squared plus 1? Okay. So du?
dx.
Okay, so if we make our substitution then, what do we end up with? Let's see, we get
Usually get
whoops. Integral of u cubed.
but you don't have a complete substitution.
But we don't, do we? Because here I've got 2x dx times another x, right? So if I try to do a complete substitution here, I end up with an x du, don't I? An extra x. So at this point, all we can say about that is, didn't work. That's not, right? So this is one that we can't do with the u substitution. Could we do this one a different way? Well, what way could I do? Expand it, and, right? I could expand this one and write it as a polynomial, and then just take, just do each power function, each term in the polynomial separately. Now, so I could do it the old way, it would work, right, without the u substitution. But that's one where u substitution didn't work, right?
Yeah, like what?
Say it again.
Why that X got there.
Well, okay, why'd the x get there? Okay, yeah, you bet. So what about this from right here? Isn't that the same thing as 2x dx times x?
Oh, okay. Why didn't we put 2x dx in the du? Can we not?
We did. So this is the du,
Oh.
right? But this is this extra x that went unaccounted for.
Can we just account for it?
No, we can't, because you see, there's no way for us to conveniently turn that over into a u, because this substitution is not easy to solve for x in terms of u. So this is an example where, and does it make sense that u substitution really is only useful if we're able to completely transition from x's to u's, right? If that doesn't work, or if doing that doesn't make the integral any easier, And a U substitution is just a strategy that didn't pay off for us, right? Now, there are a host of other strategies. We've got, I don't know how much of this we're gonna get through this year, but I wanna get through as much as I can. We've got, we got trig substitution possibilities, we've got integration by parts, we've got all kinds of things, there's all kinds of strategies that we can try on these things to manipulate that integrand to make the integral work. But this one fell short this time. Yeah.
Okay, what if you did powers underneath a number? Would that work?
What do you mean?
Well, never mind. Yeah, never mind.
Okay. I just want to give you one example here where U substitution, it really didn't work, and it won't always work. There'll be some times where it literally won't make things any better. Okay.
To make that work, it'd be an x cubed, correct?
Right. Now, if this were an x cubed in there, it would have worked, wouldn't it?
Yeah.
Yeah. Okay. All right. So let's try. Now I want to try next step here. I'm gonna make things just. This one's gonna work, but you're gonna have to work at it to make it work a little bit, right? So how about something like this? What if we had? We'll stick with something really familiar. So this is gonna look an awful lot like the ones we've already done. But it's not quite as fortunate. Let's see, I'll make that. We'll do that. Okay. Suggestions?
It's gonna be x squared plus 1.
Okay, that makes sense, doesn't it? Because that's the part that's being taken to the third power, right? That's inside the power function. So u equals x squared plus 1 again. And so du would be 2x dx. Okay, now let's see what we got here then. So we've got, it looks like, here's our u cubed, right? What are we left with though then?
We're gonna have an x dx.
An x dx is what we've got to substitute for, right? Now there's a bunch of ways that people teach this, but I really think this is the way to do it. This to me works the best. So if I account for the u cubed, this is the stuff that's left over. That's what I have to be able to substitute for. So the way I like to do this is I like to say, okay, if that's what we need to substitute for, let's isolate that on the right side of this substitution equation. Okay? So we're going to say, well, what is x dx, because that's what we need. What is x dx equal to in terms of du? Well, x dx just equals, what is it? du over 2. Yeah. Or 1/2 du, right? Make sense? So now we can make our substitution, can't we? Because we've got a u cubed times a 1/2 du. We'll just put the 1/2 out front.
That's snazzy.
Isn't that snazzy? Okay. And so that's one we know how to do. What's the answer?
Everybody put the 1/2 in front.
Just because it's a constant. Because it's easier to kind of, just it makes things look less complicated if you just pull that constant out front.
1/2 integral x squared plus 1 cubed.
So, right, so what's the antiderivative of u cubed? Say it again. U to the 4th over 4. Good. Plus c. Okay. So in other words, that's just 1/8 u to the 4th plus c. What's the last step? Yeah, reverse the substitution. So now we've just got 1/8 times the quantity, right here. X squared plus 1 to the 4th plus c. Okay, so it wasn't just a perfect fit. We had to multiply by a constant to get it to work in a sense, right? But we were still able to complete that substitution pretty easily. Okay, try another one. let's see. Oh yeah, here's a good one. I like this one. Okay. Okay, stare at that for a second. What do you think?
Can't you just turn it into a 1/2 power?
Yeah, we can, sure. We can make it a 1/2 power, but that still doesn't fit. It doesn't fit one of our standard forms. And do you understand what I mean by that? Right? When I say it doesn't fit a standard form, let's think of our short list of standard forms, right? Like we've got things like, for example, we know that the derivative with respect to x of x to the n equals, x to the n plus 1 over n plus 1 plus c. There's one of them we know, right? We know the derivative with respect to x of, oops, we're doing integrals, aren't we? Hang on, gotta go backwards. That's supposed to be an integral, not a derivative. What am I doing? Antiderivative. Whoops. So we've got this, right? We have that, right? Or we have this, the antiderivative of cosine x dx equals sine x plus c, right? Which one would this fit out of all those? It's the first one, isn't it? It's just a 1/2 power. Okay, but what we don't have is one of them in our, and you guys have that little list, don't you, somewhere? Did I give you a little list of the antiderivatives and derivatives? I mean, it's in the book, but I'll print it out again. I'll make some copies of that today. Remind me before the class is over. So what we don't have is one like this, the antiderivative of that, right?
Yeah.
We don't have that one. Why would we? That one's just some random one. There could be an infinite number of permutations of problems like that, right?
Mm-hmm.
So why would we happen to have just that one? Wouldn't make sense. Now this one makes sense because it's very general, right? But we don't have that one. But we could maybe fit that one to one of our standard forms by making a good U substitution. See what I'm getting at?
Yes.
Okay. So what would our U substitution be?
Once you put it
2x
1/2,
minus
you just put it in the parentheses, the 2x minus 1 into u.
Sure, okay, yeah, we could do that. And we can, if we want to rewrite this maybe like the integral of the quantity 2x minus 1 to the 1/2 dx, but it's still, so it looks like it's starting to fit the power rule, but still, we need to make a U substitution.
You take
2x minus 1, yeah. Does that make sense? The argument, whatever's inside the radical, that's what's causing the problem, isn't it? That's what's making this thing not fit, is that I have the square root of something big instead of just an x, or a u, right? Okay, so our U substitution, okay, so what's our du?
It's x
2. X
2.
cubed over 2/3.
2dx. No.
So yeah, what is it, 2 dx, right?
Where am I going? Whoops.
Okay, everybody good with that? Okay, so let's try to account for everything that we've got there then. So we've got here is our u to the 1/2, but then all I've got left is
dx.
a dx. Well, there's a dx.
But then you can make the du multiplied by 1/2.
There you go, right? So if I just divide each side by 2, I end up with dx equals 1/2 du, and now I can complete the substitution, right?
Right.
So this looks like
Just like the other one.
the integral of u to the 1/2 times dx is a 1/2, which will stick out front, du, right? Okay, what's our answer?
1/2
What's the antiderivative of u to the 1/2?
So it'd be one
Definitely,
half.
definitely.
No, it'd be 1.5.
Why is that?
I'm talking about like if you multiply the one half of the.
Okay, but how do we do an antiderivative?
N plus 1.
Yeah, never mind. A plus one, so it'd be 3 halves.
Okay, good, so it's gonna be u to the 3/2 divided by 3/2, but we instead multiply by 2/3, right? So we get 1/2 times 2/3 u to the 3/2 plus c. Good. And the 2's cancel then, right?
So you get
And so we can just reverse the substitution. Good, and we end up with 1/3 times the quantity, 2x minus 1, to the 3/2 plus c. We're done. Okay. Make sense? Getting it?
Yeah.
Okay, so we're getting there. We threw in the additional wrinkle now. We know how to, how to multiply by a constant if necessary, right? What about something like this? Here's the next potential issue we run into. How about something like, surely they must have an example like this. I would think they need to. If they don't.
Mr. Roy?
Yeah.
Go back.
Yeah.
Always, you're right, we always have that. We'll make that.
Call the, oh,
Keep forgetting to hand it back.
Yes, it's a rain day.
What the heck? Why are they gonna do that? Okay. Well, this dumb book doesn't have one of these, but I'm gonna make one up. Okay, what do you think about this one? X plus 2. Make sense?
I'm on fire. Start with the last one.
Okay, u equals x plus 2, so what's du?
1. dx.
So it should be dx.
Good, okay. So what do we end up with then? Integral of, so this part is going to become
U to the 1/2.
u to the 1/2. And then dx is going to be du. But we've still got this, we might call this naked x there, right? And that's what mathematicians sometimes refer to it. We actually need to spice things up. What do we do with that? Any suggestions? Yeah, well, no, just erasing it is not an option.
I like that
Can
idea.
you solve the x like du dx and then divide by d, so then you be x equals 0 and then you just like that?
Okay, now you're onto something, but how about if we use this substitution equation?
Yeah.
Okay, is that what you mean?
Yeah.
Yeah, why don't we just complete the substitution? Okay, and that's what I would call this. I would say at this point, we just need to complete the substitution by solving for x in terms of u, right? So what is x in terms of u?
Or U minus 2.
U minus 2, okay? So we could replace this x then.
U minus 2.
Yeah, we could replace this with a u minus 2
U to the 1.
times u to the 1/2 du. Okay, if I wanted to write that, just for a second, I'm going to write that with a radical, and I want you to compare these two things and tell me, let's just compare these right next to each other. So we started with this integral of x times the square root of x plus 2 dx, and we converted that to
U.
the integral of u minus 2 times the square root of x. Square root of u, whoops. Square root of u, yeah.
Tony, where are you?
Okay, does that seem like we didn't accomplish much there?
No.
But I would argue that we actually did accomplish a lot there. Okay, it doesn't look like we made any dramatic improvements. Each of those has the same number of variables, they still have a square root, but what's the big difference? Say it again? Yeah. What's really the problem with this original problem? The original problem that we're given, what's the issue there? Well, the issue is that I've got this x plus 2 under the radical, right? Now, if I had like an x plus 2 or a u minus 2 outside of the radical, I'm really okay, aren't I? How can I continue and solve this thing? How can we use what we've done to our advantage here? How could we? Yeah, I could just distribute this u to the 1/2 over each of these, over this polynomial, right? And I'm just going to get a u to the 3/2 minus a 2u to the 1/2. Those are, I mean, sure, they're fractional exponents. I guess that's a little bit tough, but no, it's not a big deal. We know how to handle that, though. That's just our power rule, right?
Right.
Okay. But here we didn't have that option because we can't distribute over a radical. See the difference? So even though it doesn't look like we got a lot of stuff done there, we really did. We wrote that in a much more convenient form that is now doable, right? So the u substitution worked. We did need to complete the substitution though, right? But we were able to make that work. Now compare that to the first example that we saw. Why was this one, why were we able to complete the substitution relatively easily? And in this first one that we did, way back here,
This is easy to solve for you.
it was easy to solve, right? There was an easy connection between the u and the x, right? Here there wasn't with this one, remember? X would have had to, if I wanted to solve for x here, think about that. X squared would equal u minus 1. So x would equal two different possibilities, either positive, the square root of u minus 1, or negative, the square root of u minus 1. We'd have to try them both out. That ends up becoming sort of complicated, right? So it really wasn't practically possible. We could have maybe forced it to work, but we would have had to really investigate this carefully because we'd have to use, when you start involving multiple functions instead of just one, you have to be really careful with how you execute the algebra, right? There's all kinds of rules that we got to be careful not to violate. This one just worked out great though. Okay? We won't even finish. You guys know how to finish that now, right?
Yeah.
Okay? Or do we want to finish it? So let's go ahead and finish it.
Yeah, let's do it.
Fine.
Throw up the.
Throw it up there. The last 6 minutes.
What do we got?
So then if we rewrite this as integral of u to the 3/2 minus 2u to the 1/2 du, what do we get? First term gives us
I know.
Please let this happen.
2/5 u to the 5/2. Good.
Where are you at?
Right? Minus, what about this one? Minus, I can leave that 2 there if I want. 2 times what? What's the antiderivative of u to the 1/2?
Where did 5/2
U.
3/2. U 3/2.
But 2/3, right?
Yeah.
2/3 u to the 3/2.
Right.
Okay, and plus c. Okay, so then if we reverse this, let's make that a 4/3, right? We'll reverse the substitution. We just end up with 2/5 times the quantity, what was it, x plus 2?
Right.
Got that. You got it.
We do another one?
Yeah, let's do one more of these. Okay, what about this one?
Oh gosh. 3x.
Okay, 3x?
Yeah.
Okay, let's try 3x. Good.
So there's like
Okay, no, it might help, but we're gonna learn something important from this one too. So let's make the substitution u equals 3x, so what's du?
3dx.
Okay, so if we do that substitution then, this looks like the integral of sine squared u cosine u times, all we've got is a dx though, right? So what is that gonna become?
du over 3.
Good, so 1/3 du, pull the 1/3 out front. Okay, that's good. Okay, now what? That's not one we know, is it?
Nope.
Okay, we might need to make another substitution. Okay, I'll give you a hint. Maybe this helps. And this is a good hint. In fact, you always want to do this. Whenever you have, now remember that sine squared of u is trig shorthand for what? Yeah, for the quantity sine u squared. You don't have to necessarily explicitly write it this way, but you want to always think of it that way. Does that help? So what might our next substitution, we'll call it a v substitution. What might our next substitution be then?
Sine.
No,
Or just sine.
sine u, right? Okay.
Ah,
So if we make the substitution now, v equals sine u, what's dv?
I don't like this. This is wrong.
That may be true.
Cosine u.
du, right? Does that make sense? Okay, well, look at that. There's a dv, isn't it? Right? So this looks like 1/3 integral of, what's that? V, how about that? Okay,
Hang
so
on.
what's the answer?
Hang on. Slow down.
1/3.
Yeah, let me pause for a second here. Any questions on that so
I
far?
got a question. What happened to all the u's?
What happened to all the u's?
Yeah.
Okay, well, here we have u's, but we need to make another substitution. So we said, let's make the substitution v equals sine u, because that's the argument, that's the function that's inside the other function.
So we went from x's to u's to v's.
Yep.
Are we gonna go from v's to t's and w's?
No, well, you tell me if necessary, but do we need to?
Why?
No, because finally we've got this down to an integral that we can do, right?
Yeah. Looks like we're not gonna take the test Monday.
Oh, there we go. Oh, yes.
Gotta finish this up.
I love it.
Ah,